Hello, this is Dr. Keith Schubert, and this is the first video on integer division. Before we take a look at how the computer is going to do division, we should take a look and remember how you handle division just doing it using standard long division, kind of what you would see when you were going through elementary school. So we have a divisor. In this case, we have number 8. And then there is a dividend, what we're dividing into. And we want to see how many times 8 will go into this number. Now, the typical way that you're taught to do it, and this is indeed a reasonable first approach, at least for us, and this is the way we'll kind of handle it here. There are some more advanced ones I'll mention, but it's not part of this particular class. The first one is to just go in and take a look, starting from the left-hand side of our dividend, and we subtract if our divisor is smaller than the dividend that's in there. So in this case, we've got 8, and we take a look starting from the left, get up to 9 here. So that's the first one where the divisor is less than or equal to the dividend, or at least that portion of the dividend. And so we put a 1. Yes, it has become smaller now, right above there. Subtract off our 8. We have 1 left. And then we kind of go through doing the same thing, adding it one bit at a time. Right, we had the 1, 0. Nope, not big enough. 1, 0, 1. Still not big enough. 1, 0, 1, 0. The number 10. Now we're finally big enough. So at that point, 10 is large enough. We subtract off 8, and we're left with a remainder of 2. So we have the number 9. All right, so 9 times 8, 72 plus 2, that gives us 74. If you're looking at this is in the 64 place, and this is the number 10, so that's 74. So it checks out. 74 divided by 8 gives us 9, remainder 2. That's kind of your standard deal that goes on. Now we have n-bit operands. In most cases, we're going to be dealing with 32 at the moment, but a lot of machines are 64-bit. What we're saying at this moment is we're going to be dealing with both divisors and dividends that are going to be n bits, 32 or 64. And our quotient and remainder, the two answers, are also going to be 32 bits. Now in this case, the example is larger. Part of this is because I'm using the standard slides here at the moment for the book, and in these ones they gave you a larger example that goes into it. But typically what we're actually going to have, and actually this is what if you take a look at the div command or div1 divide for unsigned, only allows you to have a 32-bit in both divisor and dividend. So this is kind of the standard approach that goes in. We call this restoring division, and that basic idea is we're going to actually go through and have to, instead of just taking a look at each of these successfully, we said, oh look, 9's the first time it's bigger. In reality, it's going to go 1 minus 8, and it's going to get negative 7. And we go, oh, that's negative, and it will add the 8 back in to 8 to negative 7 to get the 1 back, and then it'll take a look and go 2 minus 8. And it'll keep going, because remember, machines cannot just guess. Well, that's not totally true. We do actually teach them how to guess, but it's got to be an organized, logical guess. So in this case, it can't just look and know what to do. We have to tell it exactly what to handle in this case. So this is called restoring division, where if it turns out that the result was negative, it was less, we would put it back and then keep adding more digits. There is actually a non-restoring division, and as long as the guess is somewhat close, we're able to make the correction to them, and then we have good ways to figure out how to guess correctly. This allows you to do very fast arithmetic. Since we're only more concerned with getting arithmetic that works, we're not going to worry about the non-restoring division. There are some very good algorithms out there. The most common one that people use actually for fast division at the moment is SRT, and there's several variants of SRT that's out there. SRT is an acronym for the names of the guys who invented it. So, In any case, we're going to only worry about restoring division completely safe. Side note, SRT is actually linked with the Pentium error if you're interested. There's other techniques to do division and floating point. We often will use approximation techniques. That's usually covered in a numerical algebra course, or it'll sometimes be called scientific computing depending on where you take them. Sign division, what we're going to do is just like we talked about with multiplication before Booth's algorithm. We're just going to say, hey, look, if you've got sign division, we're just going to take the absolute values, do division there, and we'll record the number of minus signs and then appropriately shift them as it goes. So it's going to just be basically handling absolute values, and then you change the signs. So we're not going to worry too much about that. Now, this first one is actually, nobody does it, but it's designed to look just like we had before. If you remember here, let me go real quick. This is a large number, and in this particular case, we've got 7 bits here. We've got a 4-bit number that's coming in, and you could actually take and subtract from each one of these successfully, kind of moving your way left to right. Well, when you consider this, if I take a 64-bit divisor and I initially put the 8 in the left half, and then I keep shifting it to the right, it'll do the same effect as if I'm subtracting 8 here. I could shift 1. Nope, didn't work. Shift 2, didn't work. Shift 3, oh, there it is, shift 3, it works. And away I go. So that repeated kind of stick it on the left and shift is designed to look just like the pattern of how you do the subtractions. And indeed, we've got a 64-bit ALU here, which is only going to be doing subtraction basically as far as we're concerned. There, for the restoring part we could add, but it's basically for the subtraction portion. The remainder part is handling what's underneath all the partial products, so all these down here, and it initially really has the whole number and you just subtract that part, but you keep moving down. Well, that's handled by having a remainder that holds all 64 bits. And then we can actually take a look at what that number is, test the bits, and just insert should we have put a 0 or a 1. This is this kind of top here. Should we put a 1? It worked. 0, it didn't work. So on and so forth. So that's kind of where this design is going through. So you can kind of see how it goes. So we have to shift these, and we do subtractions. If we have to restore, we have to add it back in. So then it'll be told to do an addition. And the right means just update from the result. So that's the hardware that's going on. And you can see the algorithm goes in, and it basically, it says subtracts. If the remainder is positive, then it was good. And so now you take a look at shifting the quotient and putting the 1 in. So otherwise you restore the value and then shift the divisor and move on. The problem with this is, if I'm just dealing with a 32-bit number, which will be in the left half here, I gotta have a 64-bit register here, I have a 64-bit ALU, and as you add those bits, remember, adders, subtractors have a linear complexity, so that makes this take twice as long as a 32-bit adder, which is all I should really need. So then we come up with a second idea. We say, hey, look, I'll take my 32-bit divisor, and this time I'll put the answer into the remainder, and then I'll keep shifting things in. This is just like the multiplication. If you remember, we notice instead of shifting this one over, I can start the number I'm going to divide by here and shift it in. So if I have the number, whatever, say 12 here, 1, 1, 0, 0, I could shift it in, and you'd only see the first bit first. I could calculate on that and see, was it okay? If not, I shift it in, 1, 1. So that allowed me to do the same thing, but now I only need a 32-bit ALU and divisor. So this makes it a lot better. Not only that, it's the same exact shape as the multiplier was, which means I can use the same circuit to do division as I could for multiplication. That's a big help to us as it goes. So that's our kind of key thing here. If I want to go faster, we have to note you can't use standard parallel hardware as we did inside the multiplier because subtraction is conditional on the sign of the remainder. So it's not quite as easy to do division as it is to do multiplication. And there are a lot of ones. The book mentions the SRT that goes in here. There's several other styles. There's also SRT is really fast. There's also ones where you can do multiplication and check, kind of guess and check type things. Those ones tend to be logarithmic in complexity. There's a variety of different ones that go on, but it generates multiple bits. You got to pick them. It still requires multiple steps, but you can get quite a bit quicker. So we're going to go into taking a look at what MIPS does, and then we'll do an example. MIPS will again use that high-low that was the result. The high 32 bits will hold the remainder, and we'll show you why that comes in. And then the quotient will be held in low. So you actually, when you do div, or div1 for unsigned, so this is signed, and you give it its two numbers that come in, you're going to end up doing both division and modulus. So this is the result of div, this is mod. And so you use move from high if what you wanted was mod, and you use move from low if what you wanted was div. So you just tell it to divide the two numbers and go from there. It doesn't do any of the checking for you. Divide by 0, overflow, forget that. That's your job. You have to handle it in software. Now, different pieces of hardware will handle different rules in here, so you just have to check up whenever you're working on a particular machine, what does it do? Will it do the checks for you or not? So let's actually take a look at how this is going on, and we'll consider 11 divided by 3. So we have high-low. Remember, high holds the remainder, low will hold the quotient. Our divisor is 3. There it is. Setup, we're going to put 11, which is 1, 0, 1, 1, in low. And then high is just cleared. So this is just gets us ready to do our calculation. Now the first thing we're going to do is we're going to shift in our first digit. So this is a shift left logical, and we're shifting both high and low. It's kind of as one big unit. So if you watch, that one drops off, this 0 moves over, so on and so forth. The first one comes across, and then 0, 1, 1, and then since it's a logical shift, the 0 comes in. So this is our new number. To this, we're going to want to subtract the divisor from high. This is how we do our check. We subtract the divisor and we see if it works. Now, 1 minus 3 is going to give me negative 2. Now, technically what we do is we are using the 2's complement of 3 and adding it, but simple enough to understand and read here that 1 minus 3 gives me negative 2. That's a negative number. So since it's a negative number, I'm going to restore. This is why it's called a restoring division process. And so I'm going to leave it alone, just put it back to where it was, but I'm shifted over. I've checked to see, shifted one position. Could I do it? This is my quotient starting to come in. No, it wasn't the right size. So the second bit, and we'll do this, I've kind of broken it up into 1, 2, 3, you can see the white lines, 4 little regions of 3, because it's 4-bit numbers. So you do this the same number of times as you have bits. So I need to shift left, the 1 moves over, the 0 from here comes in, and then the 1, 1, 0 goes over and 0 comes in, because it's a shift left logical. Then, next step, I have to subtract from high, there's high, minus 3, so it's 2 minus 3, and I get negative 1. It is negative, so that's telling us that this is not going to be big enough. So we have to restore, since it's less than 0. We have to add the divisor back, and it actually does put it back through as an addition and come back out. And we'll get 2 here, and then this stays exactly the same. Now at this point we'll shift left again. Now we've got 5. So we initially had 1, it shifted in. We had 2. Now the 1, 0, 1 comes across, 1 comes down, 0's the rest. This is now 5. 5 minus 3, our next step, gives us 2. So it's now positive as a result. Again, this stays the same. But since it's a positive result, it's greater than or equal to 0, we're going to set the least significant bit of low to 1. Remember, these digits coming in here, initially here when I shift it, we presume it didn't fit and we put a 0. It's also because it's kind of shift left logical. I could have said I'm writing a 0 because there was nothing there, but why do extra work? I shifted again, that 0 moved over. I didn't need to do anything because it didn't fit. Those 2 zeros moved over. We're guessing it won't fit, but it ends up fitting. So we have to set it to 1. So 0, 0, 1. These are the first 3 of the 4 bits of our quotient. It did actually fit. That's why we have to set that bit to 1, because when we subtracted 3, we had 2 left over. Now we'll shift it. The 2 shifts over. The 1 comes across. So we have 5 again. These shift over, so that 0, 0, 1, and a 0 comes in. We subtract 3 from 5 and we get 2. And then we can note 2 is positive, so we keep it. But again, we have to set the least significant bit of low here to 1 because it worked. So what we're left with is 11 divided by 3 goes in 3 times with a remainder of 2. 3 times 3 is 9, plus 2 is 11. So indeed it does work for us. So that's good. We're happy. Division works. What I'll do is the next couple videos I'll make other examples, give you 2 more of how this division process works, and then we'll take a look at floating point in the following ones. So hope this helped you out, and I will see you on Monday.